Hi everyone. My name is Nomsa from the University of Pretoria, and today I'll be sharing, I'll be presenting the findings from the spatial distribution assessment of CAMEX simulated concentrations of ground level ozone across South Africa. So first of all, I would like to acknowledge the following institutions starting with the NRF for funding my master's project, and the ADSA, which my project was part of, and all the collaborators in the larger project. So I would also like to acknowledge ESCOM for funding my attendance at this conference. So as I've already mentioned, my master's work formed part of a larger multi-institutional and interdisciplinary research that focused on nitrogen biogeochemical cycling across South Africa. So this was a nationwide assessment. So my master's work contributed towards understanding the atmospheric component cycled in red over them. So what is the problem? So majority of the studies in South Africa focused on assessing atmospheric or ambient concentrations of pollutants in the industrialized region. And this has, however, left a gap in understanding how these pollutants are distributed spatially across South Africa, including the non-industrialized regions of the country. Therefore, as my master's work focused on assessing these ambient concentrations and spatial trends of nitrogen dioxide, ozone, ammonia, and nitric acid across South Africa as part of the larger project using a comprehensive air quality model with extension. So it was a nationwide assessment. So we first looked at the available measurements of ozone across the Saki stations, FTON and Sakis, and BioGrip sites. And then secondly, we assessed how CAMEX performs in simulating the concentrations of these pollutants across South Africa. And then afterward, we used the simulated concentrations to see how nitrogen dioxide, ozone, ammonia, and nitric acid are distributed spatially across the country. However, for this presentation, I will only be looking at ozone. Why ozone? Majority of the studies in South Africa have shown that ozone is associated or linked with multiple health. It has multiple health impacts from your cardiovascular diseases as well as respiratory related issues, as well as environmental implications. And also, most of the studies have shown that ozone is a bit difficult to bring into compliance with the air quality standards of the country. So in most studies, we see higher or increased level of ozone in background sites or receptor sites. Hence, hence the study in background sites or downwinds of the major sources. So because of the nature of the work, we considered multiple data sets from different infrastructures, starting with the Sakis. Initially, we had 85 Saki stations. However, after quality control, we were left with 37 stations for analysis. This was after we also applied 60% data capture, because 75 was a bit higher and we were losing a lot of stations. So the data that we got from the Sakis was nitrogen dioxide and ozone measurements at an hourly resolution for 2022 and 2023. So we also used the two infrastructures, the FTON and BioGrip sites, to represent the background conditions of the country, or the less polluted regions of the country. So we used 4 FTON sites and 1 BioGrip site, which is Velgegrond, and the passive data was nitrogen dioxide, ammonia, nitric acid, and ozone. So the resolution was in monthly resolution from 2022 September to 2023. And we also used the simulated concentrations using CAMEX, which was nationally run by the CCR, and the model output similar with those ones that I've already mentioned at an hourly temporal resolution. And the inputs for the meteorological fields, we used the inputs from the WAF model, and then for the emission inventory, it was a locally developed emission inventory by the CCR for both 2022 and 2023. So this is just an overview of how the stations are distributed. In green, it was before the quality control, and then in blue over there are the stations that we considered for the analysis going forward, and in yellow are the stations that we had to let go because of the data capture. So it's just all of our stations spatially distributed. As you can see over there, we have the FTN sites, the Bagrip sites, as well as the Saki stations, the Spionkop, Skukuza, Kimberley, and Jonkeshoek. These are the stations that we looked at. So we looked at the diurnal and seasonal cycles, and we also compared for annual averages and seasonal averages. And due to the differences in the temporal resolution, we had to time match the model output with the available measurements to be able to assess how CAMEX performs in simulating these concentrations. These are the statistical parameters that we used, and then after this analysis, we used the simulated concentrations to see how these pollutants are distributed across the country. So here you're just looking at the diurnal and the seasonal cycles of ozone across South Africa, grouped according to the province at the ozone diurnal cycles. As you can see over there, we have lowest concentrations of, at night, and even lower during the morning hours due to the traffic or the morning rush hour. And then we see the afternoon peak over there as a result of increased photochemistry as well as, or as a result of increased photochemistry. And then in the seasonal cycles, we can see we have lower concentrations in June or in winter, and then the ozone peaks in spring over there. And this is common in the continental South Africa, as during winter we have highest emissions of nitrogen monoxide, which titrates ozone. And then during spring, the peak over there, it's due to the regional biomass burning in the country. So here's the performance evaluation for CAMEX at the Saki stations. I know the numbers are very small. However, you're just looking at the color coding over there. So in green are the stations with the different percentages of less than 50%. In yellow, it's between 50 and 70. And in green over there, in red over there are the significant differences of greater than 70%. And then in general, the model overestimated at most of the stations, the MB is greater than 0. This means that the model simulated higher concentrations as compared to the measurements. So when we're looking at the averages, as you can see over there in green, most of the stations are in green. This shows that the differences are less than 50% at most of the stations, and we have significant differences at only 2 sites, and then those ones who are moderate, fewer as well. And this applies as well to the variability. The model was able to simulate the variability in the measurements. And looking at the variation as well, we had strong relationships across the stations, which shows that the model was able to simulate the ups and downs of the measurements. And then in general or overall, the model did perform well in simulating the concentrations of ozone at most of the stations, and this was also evidenced by the lower mean absolute errors as well as the mean biases. So this is the performance at the backgrounds or the remote sites, and the model underestimated O3 as compared to the Sakis. This means that the model simulated lower concentrations as compared to the measurements. And when we're looking at the averages, it did get the averages, or it did get the averages are comparable with the measurements. However, this is different for the variability. As you can see over there, we have 2 stations with variability of greater than 70%. 2 stations, it's just at 1 station that the model did get the variability of the concentrations. And then in terms of the relationship, there were weak relationship at most stations except for 1 station, which is Jonkeshoek. So in general, the model performed better at the Saki stations as compared to the background sites. So here we just compared the simulated concentrations of Spatial with the average concentrations across the FTN Sakis and the Bagrip sites during summertime. Why summertime? It is because of the different data set that was available. So this was just the common period that we had data for all of the Saki stations as well as the bi-grip sites. So we time match this with them, simulate the model output, and then in general, the model did well, even at the Saki stations, even at the FTON sites, simulating the spatial distribution of ozone at this period at all of the sites, at most of the stations. As you can see, we saw that higher concentrations, the model did get the higher observations as well, so they were comparable. So what you're looking at here is the spatial distribution of the simulated concentrations of ozone, and I'm only presenting the ozone one here. However, what we found here is that most of the highest O3 or ozone concentrations were found in areas surrounding regions of higher NO2 emissions. This just shows that the high emissions in the industrialized region does affect the regions or surrounding regions or regions downwind of the significant sources or in receptor sites. So we can also, here, this is the same, it's comparable with the seasonal one that seasonal are cycles at the Saki stations. As you can see, we're seeing peaks in ozone in spring, which coincides with the biomass burning season in this country. So this study recommends continuous monitoring of ozone in the receptor sites or in the background sites. And the future work will build on conducting sensitivity analysis to identify the main drivers of ozone in this country, which will be able to guide the design of efficient monitoring as well as strategies to manage ozone pollution in the country. Thank you.
Okay, thank you very much, Nomsa, with 2 minutes to spare. So thank you very much for that. Okay, I would like to invite our next speaker, Mr. Marutambedzi. He is from